Hello everyone, welcome to my next tutorial 1.3 White OLED simulation. As before, in the previous discussion, I have already completed 1.1 light emitting device simulation and second tutorial 1.2 electronic OLED simulation. We have simulated their pulse current operation and current voltage curve and transient analysis and optoelectronic coupling also occurred by us. In this tutorial, we will be studying about white OLED simulation structure. So before start of my tutorial 1.3 white OLED structure simulation, I want to introduce myself. I am Sahil Verma, application engineer of the well-known company Impulse Technology. And now move at the next slides. Our company have partnership with Nano Academics, which is Canada-based company which offers several software like Nano Decal, Rescue, KittyCat, and also well-known company Metra, which is USA-based company, and Fluxim. At here we are discussing about Setfos software, which is developed by Fluxim company. Our company provides many of the services: software distributor, training program, technical supports, and equipment like microprobe stations, solar cell, thin film, FET, gas sensor, transistor. For more detail, you can check our company website impulsetechnology.in. In my first playlist video, I have already tell all about my company infrastructure. So you can go and see at here about the Setfox software and Fluxim company. Our company also have valuable customers like IIT Guwahati, IIT Madras, IIT Dhanbad, IISER Kolkata. Number of customers are present. So now I am going to discuss about white OLED simulations. White organic light emitting devices are flat, ultra-thin devices that emit white light. They are made of organic semiconductor sandwiches between two electrodes. When an electrical current passes through the organic layers, the device generates light. We are going to simulate at here the charge transports and excitant transport equation. We couple the obtained excitant profile respectively, calculated radiated dipole profile to optics to simulate also the light outcoupling. So now I am going to go for the from the tutorial. So now I will be open Setbox software. Click at the right side and run as an administrator. It is a new feature which will be found in Setfox 5.5. At here, new dropping model are introduced. I have already at the first video explained about all of the geographical user interface of the Setfox. I discussed all of the tools and their parameters, how we can put. So you can go with my first playlist video to more updates and you can get all information about my Setfox GUI. So at here I want to create file as white OLED structure. So I click at the new create simulation tab and through the plus I number of the layer structures I will be add. Now I will be give name one by one. Air top, due to the complexity of the layer structure, we can also load simulation example full OLED white parts from the example database as number of the examples are given. So full load white parts we can load, but I'm here give the each layer name so you can get more clear vision. Glass, ITU, Nestify, Alpha NPD. Don't mention a special character, and otherwise it will be so invalid layer name. GTCTA. You can give each layer one by one. TCTA. 'You can add more layer because calcium and aluminum are also present here. Air bottom. Now you will mention each of the layer thickness. Top and bottom layer are semi-infinite medium, so thickness are irrelevant at here. Micrometer units you consider at here. Twenty mm, 10 mm, 3 mm, 15 mm, 10, 40. It totally depends on you what thickness you want. You can see at here layer structures. When you change with thickness, the layer structures are automatically changes. Glass layer is coherent and we want to calculate the light emission of the OLED into the top air layer. As we know, the electrical part of OLED comprises of hole and electron transport layer as well as 3 emitter material like red material and green material and Spyro it is a blue material. We can also see it here. White OLED stack is enclosed between two air layers at the top and bottom. Now I will be imports refractive index of the medium. Which material show the dispersion and wavelength dependent when we will be imports refractive index. So you can imports at here ITO. NHT5, alpha NPD, imported at here will be same. It is a polymers. We imports polymer 5 pfb.nk at here also pfb.nk file formats. Beta spiro.nk file format. You can make your own layer also at the notepad tab, and you can export at here. Setfos also give availability of create your own file. Beta spiro.dpvbink. Also for the calcium, ammonium. Similarly, we can import all of the file, but it will be .nk file format. So at here, layer structure are completed with the refractive index above, but we need to define also electrical properties of the material. At here, we also need to mention work function, NPD, general tab, we activated semiconducting material. We will be imports .em file format, electrical mechanical properties, because it is a semiconducting material. PNHT5, we need to activate general tab at electrode at here, because semiconducting materials layer always is hit between two electrodes. And also mention at here work function 5 electron volt. In alpha NPD, we need to activate semiconducting layer and activate general tab. If you import semiconducting alpha npd.am file format, you can see at here value. Mobility model consider at here EGDM. EGDM stands for Standard Gaussian Disorder Model, which is model that account for the carrier density dependence of mobility. It is often used in device simulation algorithm. Now we activate at general tab R alpha for the red material and import your file. You can see it here .mm file formats and can import. Exciton at here mention radioactive decay rate, general efficiency, diffusion constant. You can see at here value. Now move at the green material and activate semiconducting tab and import their file. When you import your file, the automatic it can be filled. If you want import your own data, you can also give through the sports tab. You can create own file as per your need. Each value already mentioned at here. Now at the TCTA, we activate general tab. Also import their file. At here mod7.em file format. We will be imports that here. You can see at here in center not mentions trap, mobile and recombinations. Spyro activate semiconducting tabs and import their file. You can see at here data automatically fill. Now net 5 similarly process occur. You can see at here discretization elements, distribution with trap energy, energy distribution, trap density, electron capture rates. It means how electron attracted by the nucleus. As we have imported refractive index files at net 5s, now we will be tick at the general tab because we need to define two electrodes and semiconducting layer in between this. For function you can also give at here. Now you need to activate emitter tab, bulb like symbol, emission module you can activate at here. As we know, electrical part of OLED comprise hole and electron transport layer. So three emitter layer that we are mentioned at here. So we will be activated emitter tab and import their file. It is a red material, so red.pl file. It is a photoluminescentrum file. Format supports that here. So .pl file imported at here. Unit consider it will be probability. Exciton coupled. Similarly activate at here emitter tab for GTCTA. and import their file. It is a supported .pl file formats. Spyro activate emitter file. It is a blue material file. Alpha and PL file we can import. Unit consider probability. At here also unit consider probability. Exciton coupled. Similarly at here unit consider probability and exciton coupled. You can see at here number of the delta, exponential, Gaussian, absorption coupled, recombination coupled, master equation exciton coupled, and you can also import at here file formats. Dipole orientation, consider isotropic. Now you can mention at here emission settings. It will be more considered spectral wavelength. Shift at here 380 to 780. If you want to shift move another parameter, you can also shift wavelength 550 nm, emission angle 0 degree. At the drift diffusion settings, number of modes presents, but considering at here steady states. At general tab, voltage can be mentioned at here 11.5, temperature 295. We will be enable at here trapping excitant because we have already give their parameter, give that parameter. Enforce global mobility, EGDM, and export the result ASICI formats. And here data also given for the 3D geometry if you want. It will be for the scattering modules. Number of the tools given. You can shift your parameter. You can also optimize for the emission mode. You can fit at here for the better accuracy and better results. That parameter you can use. Master equations for the outcoupling. Now at here we need to mention discretization. So at discretization is the process of converting continuous data into discrete categories or intervals. It is a technique to use in data analysis to reduce the amount of data, simplify it and make it more suitable analysis. So at here alpha and PD discretization delta elements I'm considering at here 30. At here discretization at element consider also 30. At discretization at element also consider 30. At same at here and it at here elements consider 45. At here discretization consider 30. So now we'll check one more time. If you do any mistakes you can correct it. At here you can see the both layer contains same refractive index but it look like a different. So we will be check at here. I think I imported at here that NBPP, but we need to import at here and pvp.nk. Similarly we check all of the settings and at the drift division number of iteration will be shift at 1. You can also maximize if you want, but it take more time for the calculation. Now you can give your simulation name white OLED simulation. I have already run the simulations, so we can give it X. So you can see it here, emitted, it is a white color. To check the correspondings, go to the CIE color, a CIE color diagram. You can see it here, white OLED, emitted, band diagram, charge density, current, electrical field, exciton density, exciton rate, exciton transfer rate, mobile teach, potential, recombination, absolute error, damping factor, residual error, and optical profiles like radiating dipole density, radiative rate profile, refractive index, absorption, reflectance, transmittance, and spectral emissions also given at here, emission, normalized emission, and white emission. So white OLED simulation with a color filter. In order to simulate a red, green, and blue display pixel, we put a color filter in between air top and glass layer. So we need to add one more layer. It will be a color filter. Color filter. Give it here 20 nm thickness, and we need to import that here cfgreen.encap file format. So import that here. So now you will be give new name full white OLED and run the simulation. Now you can see that here emitted it is a green line color, and the properties also mentioned at here, charge density band diagrams related, and the CI color diagrams, it will be green. So all of the properties you can see at here. Similarly, white emissions, normalized emission, it is a x-axis, y-axis at given at here. You can change at log, inverse. I think you understand my tutorials, and white OLED structure simulation with color filters. So at here I end my tutorials, and if you want more information and you have any query, please contact impulsetechnology.in, and my email also given at the description box. So thank you.